All right, today we're talking about our final unit, recursion. All right, today we're talking about our final unit, recursion. All right, so recursion is going to be a very similar topic to looping. Remember way back to our classes, unit 4, we talked about using loops to accomplish a task by doing something over and over and over again. So if I want to sum the numbers from 0 through 10, I'm going to create some sum variable and then use a for loop and then have I increase by 1 each time, having the values 0, 1, 2, 3, 4 all the way through 10. And I add those to my sum, and that will get me that sum value. So recursion is an alternative way for us to do iteration. And the way that it works is it makes a method call itself over and over and over again. So when I build a recursive method, I'm going to be breaking the problem down into simpler and simpler, similar subproblems of the same form. And eventually, our problem is going to get so small, so simple, that it's very easy to solve. So let's say we want to recursively sum from 1 through 10. What is, like, if we're just doing the math, what does summing from 1 to 10 look like? Yeah, 1 plus 2 plus 3 plus 4, all the way up until 10. And I can write that the other direction as well, 10 plus 9 plus 8, etc. So if we look at this equation, 10 plus 9 plus 8, etc., we can kind of say that this section starting from 9 going downward, 9 plus 8 plus 7 plus 6, that's the sum up until 9, right? So we can say that the sum of 10 is equal to 10 plus the sum of 9. So we now have a smaller problem. We can say the sum of 9 is that same thing, and then we can say that that subsection, 8 all the way down to 1, is the sum of 8. And we can keep doing this until we get down to the sum of 1. So each time, our problem is becoming slightly simpler until we reach a point where our problem is as simple as it's going to become. Because the sum of 1, there's only one number to add to itself, and it's the number 1. So the sum of 1, we're not going to call the sum method anymore. The sum of 1 is always going to be 1. So this is our simplest solution. So when our problem reaches a point where we cannot simplify it anymore, this is called the base case. So my base case for the sum method here is when my number is 1, the value that I give back is just equal to 1. And then we can file back up the chain. Sum of 2 was equal to 2 plus the sum of 1. And so that's going to give me 2 plus 1 gives me 3. And I follow that back up the chain until I get all the way back to the sum of 10. So any other step in this process, we can use this more generic formula where for any number that isn't 1, the sum up until that number is equal to that number plus the sum up until the previous number. So the sum of 10 was 10 plus the sum of 9, the sum of 9 was 9 plus the sum of 8, etc. So let's actually build that method in code and see what that looks like. So I've got my public int sum, and I'm getting an n as a parameter. So we're going to start by adding that base case to our method. The base case is how our recursion, how our looping essentially is going to stop. So if our n is equal to 1, then we're going to return 1. The value for sum of 1 equals 1. So we're going to return that specific value because that's what it is. That's what we get. And then we're going to add our generic formula to find that sum. So if our n was not equal to 1, we're going to return from our method the sum of our current value n plus we're going to call sum on n minus 1. So we're going to repeatedly call this method until sum equals 1, and then we're going to fall back through the chain. Yes?
Well, so for like a base case, are we always given some sort of like base, or is it like basically easy to figure out? Because like,
So depending on the different problem, you're going to have different kinds of base cases,
right.
but you'll always need to have some sort of simplest answer that doesn't call the method anymore.
So 0 can also work as a base case?
Absolutely, yeah. So depending on the problem that you're working with, your base case would be different in different scenarios. Good question, though. All right, so let's say we are calling our sum method and we're trying to find the sum of 5. So from our main method, we're calling sum of 5. So we've got 5 is the value for n. 5 does not equal 1, so our condition for the if is false. So we're going to call sum of n minus 1. Current value of n is 5. Sum of n minus 1 is 4. So we're going to call sum of 4. So before sum of 5 can finish, we have to finish running sum of 4. Because we just called that method. We have to finish that second method call before we can finish the first one. So now we're in sum where n equals 4. N still doesn't equal 1. So then we're going to call sum of n minus 1 again. We're going to get called sum of 3. Still doesn't equal 1, so we're going to call sum of 2, and we're going to call sum of 1. But now n does equal 1. So we're going to return 1 out of our sum of 1. So we're going to return 1 to our sum of 2. So when we go back to the sum of 2 method, that sum of n minus 1 value, that's equal to 1. So we can add 2 plus 1, that gives us 3. So we'll return 3 from sum of 2. Now that sum of n minus 1 is equal to 3, and we can keep going. 3 plus 3 is 6, we return 6. 4 plus 6 is 10, we return that value. 5 plus 10 is 15, we return that value from our sum. Yes?
How efficient are these methods?
They're generally pretty efficient, I think.
It's like, aren't you running the same thing? Like,
You are calling the same method over and over, yes.
so I guess it just depends on the values.
So it would depend on how efficient the code inside of a leaf is. Just like any other kind of looping or iteration. So once we have finished calling all of our recursive methods, our sum of n equaling 5, that returned 15. So we can just print that and print that 15 out. So each recursive call of our sum method is going to have its own set of local variables, and that includes those formal parameters. So within each of these, my formal parameter n had a different value, and it wouldn't really work having that recursion happen if my formal parameters were not different each time. Because if nothing changes, nothing is going to be able to stop the recursion from happening and going forever. So when we have a recursive function, recursive method, we need to make sure that the parameter we're passing is changing somehow through each time we call the method so that we can actually hit that base case. If we look at this stack, and I'll explain the stack a little bit next slide, we can see our sum method was called 5 times before we hit that base case. And then we can look at those values of our formal parameter each time to see how it progressed through our recursion. So this recursive method is going to accomplish the same goal as our loop from earlier, that for loop that was just adding with I equaling 1, I equaling 2, I equaling 3, etc. It just does it in its own unique way. So the stack is this kind of virtual construct that is created anytime we call any method. It hasn't been super relevant up until now because during recursion is when it really matters. But anytime we call a new method, it gets put on top of this stack. And once that method has finished its execution, we're going to take it off the stack and then execute the next thing that was on top of the stack, which is where that method was called from. So this is actually kind of upside down to being on top. Here, I guess the bottom is the thing that's going to execute first. But I can't finish sum of 2 until sum of 1 is finished. And I can't finish sum of 3 until sum of 2 is finished. So we have to finish the bottommost thing, or I guess the topmost thing on our stack. And then we can finish the next topmost thing, and then the next, and the next. So whatever went in most recently is going to be what finishes first. So when we use recursive methods, keeping track of this stack is important because it's going to tell us which methods are going to be executed in what order once we've reached our base case. So this recursive method is pretty simple, but if we start branching out into more complex recursion, it's going to be important to kind of keep track of how our stack looks. All right, so we can also use recursion to traverse through various different kinds of collections, like strings, arrays, or array lists. Strings are a collection of characters, and then arrays or array lists, we have whatever kind of collection we want. So let's say we want to sum all of the values in an array from the beginning up until a target index. So if I have my array, my nums, holding 8, 3, 5, 2, 7, and I want to call sum array with my nums and 3 being that last index that I want to sum up until. So if we want our method to be recursive, like I said before, A, we're going to need to call it from within itself, and B, something about the parameters is going to have to change each time. So if we look at my nums, since it's an array, we're not allowed to change its size. So we're going to need to change that index each time we go through our recursion. So if we want to sum all the elements up until a specified index, this is very similar to our summing up until 10. You can say our equation is the value at the current index plus the sum of everything up until the index beforehand. So in sum of index 3 plus sum of index 2. So our base case here would be when that index hits 0, because that's the lowest index in our array, and there's no other elements to sum together with. So if my index equals 0, this is my base case, then we're going to return my nums at index 0. If we hit that lowest point, we're going to return the value at that index. Otherwise, we're going to do that other. We're going to say nums at my current index plus, we're going to call our summary method again with that same array, and we're going to pass index -1 so that our index changes each time we call the method. So here's that main method code that I had before on that same method. So in my main method, I'm going to call sum array with the parameter 3 for my index. I'm just going to include the index in my little boxes here because the array isn't going to change each time. So it's less relevant for my little boxes here. So my index is 3, doesn't equal 0. So we're going to call sum array with our same nums array and index -1, so 2. We're going to be in n equals 2, or index equals 2. We're going to keep doing this until we hit our base case. We're going to build our stack. We're going to call sum array over and over again until index equals 0, at which point we will return 8, because that is at nums at index 0. So we return 8. So when index was equal to 1, our method called for sum array at 0 is equal to 8. So we're going to add 3 plus 8 is 11. 5 plus 11 is 16. 16 plus 2 is 18. So once we've finished executing all those methods, we've gone back up the stack, we're back in main. We can just print 18, and that'll print out the value we got from that method call. So recap. A recursive method is a method that is going to call itself to perform iteration, to do some kind of task over and over. We can use recursion to help take a complex problem and make it simpler each time we call it. And once we reach a point where our problem cannot become any simpler, and it's different for each different kind of problem we work on, we've reached that base case. And every recursive method needs to have some kind of a base case in order to stop iterating. Otherwise, it'll loop forever and your program will crash. We want to avoid that. And we can often write our recursive problems as an iterative loop instead of as a recursive method. However, recursion is definitely useful, more useful than loops in various different scenarios. There's places where it makes more sense to use recursion. And we'll get into that in the next couple of classes. So, any questions before I open that module for you? Cool.